As we discussed in the last lecture about the introduction of the what is data management system. So now we are moving towards the second lecture, which is about data models. Main idea of this lecture is we are going to discuss the three core concepts. It is what is a conceptual data model, logical data model, and physical data model. So it is in the decreasing order. So we are coming from the conceptual, it's more higher, logical, it is intermediate, and physical is the lowest. So these are the three models, which is quite famous. So starting with the first one, it is very quite a short representation of the whole models. So if we see the levels of conceptual, then logical, then physical, in each one description alongside its abstraction and examples. So starting with the conceptual model, it is, as from the name, it's very clear. So it is conceptual, okay? So I mean, this is the concept of what we are introducing. High level and description of information needs not directly implemented. So this is the one, I mean, which mapping the whole database idea in higher level. So its abstraction is a higher level, okay? So the example of this one is ER, entity relationship, and it's really famous and almost every databases we are creating its entity relationship diagram. So which reflects how the data has an entities or collections or vertices or ages, and it shows the abstract picture, higher abstract pictures of the whole database. So in short term, we can see ER, the entity relationship diagram. Further, the second one is logical. So specifies how data is represented and operations, what the DMS expose, data management is exposes here, okay? The data is now exposing to the database here. Not here exactly, but here is the logical concept, how we will be organizing our data in the computer actually on the lowest level of abstraction. So this abstraction is middle, and the example of this one is relational tables, JSON, documents. So these are the examples how we are logically representing the data on a abstractions of a middle level. The third one is physical, and the physical is the actual representation of data, how computer stores the data, how data is physically stored at a low level. Okay, now it comes to the computer, how they are storing. Okay, but not to forget the logical aspect should be represented in the physical data, how we planned. So the idea or the examples of this one is the D trees or LSM trees or Bloom filter, paraquets, files, and many more. So these are the different data storage formats or data structures, how the computer stores the multiple data types. Okay, so in detail, we are starting with each and every one. That was in a quite quick definitions and explanations about each ones of the data models. So now we are moving toward the each one in more detail a little bit. So the first one is conceptual. Okay, the conceptual model. As we discuss this, we are discussing here entity relationship model or entity relationship diagram. So entities could be tables. In this case, we call them rectangles, relationship or lines, and plus constraints. So constraints are some type of conditions we are applying. Entities have attributes with a type, uniqueness, optionality, constraint. So further, each entities have its attributes with its own type. Okay, either it's a uniqueness or optionality or more constraint. So there are multiple relationship types when we are designing the entity relationship diagram. So we have three main relationships types, and its meaning representation is here. The first one is in the ERD diagram, we have one-to-one. So each instance of a E1 is associated with exactly one instance of a entity 2 and vice versa. So this is basically working in both way. Okay, so one instances of entity one has a directly association with the entity two, another instance. and it's vice versa. It's from both sides. Entity 2 has with the entity 1, and entity 1 has with entity 2 association. So this is called one-to-one relationship. In one-to-many, each E1 instance is links to 0, 1, or many entity instances. So each entity 2 links to exactly one entity 1. So here, what does it mean? So from one side, I mean from the entity 1 table, so we have 0, 1, many or more entity relationships with the entity 2 table. But from the other side, everyone has an only one relationship with the entity 1 table, or only one association with entity 1. The third one is N to M. It's, we call them many to many. Okay, so each entity 1 instance links to 0, 1, or many entity 2 instances, and vice versa. So in this case, what is the difference between one to many? In one to many, the entity 2 has only one relationship with the entity 1. But in this case, every entity 2 instances have a relationship with each of the entity 1. So this is called one-to-one. It's a complex one. Okay, that was a quick and short introduction about what is conceptual model, data model. The example we discussed here, it was entity relationship model. So in which we have seen entities are rectangles basically, in which we have basically our main table. Like if you take an example of the relational table, our relationships are lines through which we are representing what relationship this table has with another one. And then each line or entity has its own further types or attributes, and each attribute has its own type. So this is the overall idea of what is the conceptual entity relationship diagram example within the example. Okay, now we're discussing the logical data models. Now it is as per the 3 level of data models. So now we are in the middle abstraction. So in this one, we are discussing multiple data models like key value models. We are discussing document models, and we are also discussing relational model, and then we are discussing graph model. And then there is a comparison of all logical models, comparison in a short. So then we will be moving to the physical data models. Okay, let's start with the first one, logical data model, which is a key value model. So in the key value model, the simplest logic model, and data is equals to collection. Okay, so here we are having the concept of a key value. So one of them is key and value. And value, we have any kind of values. It is a kind of pairs. Keys are unique identifiers here. A key is not should not be equivalent. Key should not be replicated. I mean, it should be new and unique. Values are typically unstructured or untyped. Here in this case, the main difference between the document model in this one is that one, even we didn't discuss the document model. Further, we will see that the key value pair model is an extension of the document model. The values are typically here unstructured or untyped here. Okay, so you can insert any type of data. So when it comes to CROD, so CROD is basically an operation: create, read, update, delete, all by key. So when we are performing all these operations on a key value pair, it is basically done by its key, because we discussed here that the keys are unique in this key value model, and values can be replicated. So examples where it is implemented, basically Redis. So it is basically implemented in memory, RocksDB, DynamoDB. So these are the examples of using this key value model. Limitation: no native relationship support. So here we don't have any concepts of entity relationship like the conceptual model. So typically used as a cache or subcomponent. So it is more of an abstract level of in memory, and they don't have any relationship support. Okay, based on this key value model, we are introducing further the document model. So document model, we see, as we discussed before, that is an extension of the key value model. BC unit is a document. But over there, the base document, the base model was the data. Data was equivalent to collection. But here, the base unit is a document. That one was unstructured in untyped, but here it is a semi-structured or hierarchy tree of a properties and values. So any collection we are introducing here, so they have an hierarchy structure with its properties and values. Values are structured, okay, and not opaque. So in the above, we discussed that is untyped or unstructured, but here it is are structured, the values, especially we are discussing the values, which are values and properties are in hierarchy structure, semi-structure. Documents grouped in a collection with no mandatory schema. And that's why we call them document model is a schema flexible. So that is the another differentiation between the key value model. With no mandatory schema, each document can differ. So it's not necessary to be pre-introduced in the schema. It's not rigid, so you can easily change the schema as you need. Which formats are basically they are supporting? So JSON or BSN. It's a binary JSON used by MongoDB, also XML. So XML, BSN, and JSON, all of them they are using. JSON is BSN is nothing but it's a binary JSON or XML. These are two formats they are using. And examples, which databases are using the document model, the MongoDB, CouchDB, Elasticsearch, Apache Solr. So these are the databases which are using document model, logical data models. Historical ancestors, so it is hierarchical models used by IBM, IMS back in 1960. So this is all about the two concepts of logical data models, key value model, so which is we can also in short say key models, and document model we discussed here. Okay, now we are discussing the document modeling, logical data model, its relationships. So, okay, as we said, the limitation of the key value model, they don't have any relationship support. But here, the data model, the logical data model of document, they have a relationship support. So here if you see the same, they have like in the previous one we have seen in the conceptual model, and the conceptual model interrelationship diagram has its own relationship instances between two different entities. Now relationships are one-to-one, one-to-many, many-to-many, the same. But here, what is the difference between that? Here we are introducing a new concept, is called embedding. So the modeling strategy is basically, if you see one-to-one, embed all attributes of entity one and entity two in a one document. But in an entity relationship diagram, there were two different entities and totally. So now here we are embedding, I mean, get together the two entities information in a single document. So this is embedding. We are encapsulating in one-to-one, in one-to-many. So embed into two instances as a subdocument inside the entity one document. What is the difference between the one-to-one? In a one-to-one, we are putting both of the entities one and entity two in a single document. But here, the entity two instances as a subdocuments inside the entity one document. So it's called one-to-many. So, I mean, we have put it the entity two instances in the subdocument of the entity one document. Okay, so the third one is many to many, okay, into M. Use an external referencing. Basically, the document model main concept they are using, it's called embedding, but they are also using embedding referencing style also. I mean, they are doing at the same time embedding. I mean, a document is defined as a subdocument. Entity two, like in the one-to-many we have seen, the entity two instances has been defined in as a subdocument of the entity one. So they both use these two concepts of embedding and at the same time referencing. So one-to-many, sorry, many-to-many use external references, store of IDs, other documents, store IDs of other documents. Directly embedding causes infinite recursion. So this is the how they are using based on the external references store the IDs of the other documents, directly embedding, causing an infinite recursion. So here an infinite recursion occur during the many-to-many because it's many-to-many relationship and a little bit complex. We have discussed so far three data logical models, key value models, and the second one we have discussed document model, and now we are discussing the third one, and this one is a relational model. So relational model, it is proposed by Edgar Cord in 1969, implemented via SQL. So most widely used logical model example are PostgreSQL, SQLite, MySQL, MariaDB, Oracle, and DuckDB. So how this is working? So they are basically designed in alignment with the relational algebra, but we are not going more in details of those things. So we are purely understanding how relational models work. Okay, a relation is equal to table. So here relation mean table with the heading attributes plus its types. Let's suppose we have a table of a person or applicant. So we are having attributes like name, father name, surname, gender, and many more. So further we are introducing attributes types. So what is name? Name is a character, or we call them in database language varchar. So this is how we are introducing, like let's suppose if it's age, so you are saying it's an integer. Then we can also further define the number, how long integer they need to take. So this is a constraint. Okay, in a body, body means a set of tuples. So further we are introducing the relations, like as a given example of a table of the applicants. So the applicant table has or a person, it has a many attributes with its type. So all of these, like the attributes and its types, are the body. So we call it set of tuples. What is candidate key? It is a minimal set of attributes uniquely identifying each tuple. One is chosen as a primary key. In a single table, we can have multiple candidates key. It's possible, but we are choosing one of them as a primary key. So each value should not replicate it each time. I mean, each time they should have to be a new value. So like usually we see ID 1, 2, 3 like this, okay, or a serial number. So they are not repeating and they are all the time new. So we are taking them as a primary key. So if you take the mobile number, so mobile number can also be a candidate key because all of mobile numbers are changed. So we have a foreign keys. It's really important. This is through this foreign key we are referencing the other tables. Okay, when we want to join them. So attributes in R1 that correspond to a key in R2 enforce referential integrity. So we are also introducing them as a referential integrity. So we are having an attributes in a single table, like in this case, we are seeing in R1. R1 could be a table or it could be a relationship, correspond to a key in R to enforce referential integrity. So it means based on a one key, we are referencing them the other table as a foreign key. So this is another aspect of the relational model. Okay, we have some sort of types of operations in the relational model. So we have operations, symbols, and its meanings. So here we are explaining the first one, projection. So its symbol in relational model is pi br. Okay, so keep only attributes in a B from the R table. So this is an overall example meaning of the, what do you mean by projection? Projection means to show them, okay? So keep only attributes. Only attributes means let's suppose we have a table. In that table, we have multiple attributes. As I given an example about a person, okay? So name, surname, and many things. So when we are projecting them, so we say from the table R, based on this constraint, so B here is a constraint, project only this thing. So this is basically projection. So the symbols are more like relational algebra terms. So it's important to understand the concepts. The second one is selection. So sigma PR, okay? So keep tuple satisfying predicate P. So predicate P is a constraint again here. So we are only selecting those numbers to based on a conditions. Predicate P is a condition. So to satisfy the condition, and they will show like we are using in the SQL a condition select static table name. So they are taking all of them, but when we say specify the name, so here they are going to only the A table, selecting from there, okay? So there is a little bit difference from the projection in this one. Over there, we are also taking attributes using a B condition from the R table, but here we are further specifying, like keep tuple satisfying this predicate. The cross product is R is R multiply S. So these are two different tables. So all combination of tuple from R and S. So this is a cross product. So we have inner join, R join S. So it is basically joined on a match of a conditions. So from two different tables. So we are joining them on a specific conditions. Especially like in this case, if you see we have a two tables of R and S, so we are joining them on a B and D. So B and D are special IDs in these two different tables. So we call them inner join. Left outer join, so R left S. So it means it will be applying automatically the inner join plus the unmatched rows from unmatched rows, R rows from the R table. So automatically they will apply one of the inner join plus the unmatched R rows. So they will discard the null for the S columns in this case. Right outer join is the opposite of the left. So automatically here we are applying the inner join and unmatched S table rows. And we are here discarding the null for the R columns. In full outer joins means they are taking both from the left and right outer joins combined. And this is the last one we have seen. This is an operations of all the interrelationals relational model. All of them we are applying in the relational model. So when we are working on a query, I mean, we have a database, and in that database, we would like to retrieve the data. So these are certain operations, projection and selecting them, okay? Projection, show them overall, and selecting them to specify them. Then we applying cross product, and under the cross product, all of these four are coming: inner join, left outer join, right outer join, and full outer join. So SQL versus relational algebra. SQL is not equal to relational algebra here in this case. Mathematically, relational algebra do not allow any duplication, but SQL allows. So when we need a certain types of values from the database to discard certain, so then this is the usefulness of the SQL. So they say SQL is not equal to the relational algebra, and SQL relations are less. So it allows the duplicates. But mathematically, they are set. Relational algebra are sets. So SQL also its programming construct, not in relational algebra. Okay, so again, we're also having in the relational model the same relationships like above. So it starts from one to many and many to many into M. So one to n is the R2 holds a foreign key referencing R1's primary key. So this is one to one, like in relation to tables, hold a foreign key referencing the R1 stable primary key. We discussed these concepts before in the relational model, that they have a candidate key. We are introducing them as a primary key, and another is a foreign key. So it is an attribute inside the table or entity which can be referred for the inferential referential integrity. So we have many to many into M creates a junction relations R1 2 with the two foreign keys pointing to R1 in R2. So this is many to many relationship in which based on using of the a foreign key referential integrity, we are referencing of R1 R1 underscore 2 with the two foreign pointing with the two foreign keys pointing to R1 table in R2. So from both tables, they are referencing to R1 underscore 2 from the two different tables, and they are pointing out to two different tables. So this is called many to many or M to M relationship, modeling relationship. So this was overall about the relational model, how relational model works when it's designed and its important aspects we discuss, candidate keys, relation, and what is its attributes, types, and candidate keys, and certain operation. Now we are introducing the fourth one in this logical data models, and it's graph model. So extension of a document model. Now this is an extension of document. We say key value pair. So after that, we introduce the document. So document is an extension of the key value pair, but now graph is an extension of the document. Extension of the document model, which are two document classes. So basically they have two document classes. One of them is called vertices. Vertices is nothing but entities or tables like in SQL. In ages are relationships. So relationships which we were introducing in logical concepts with the lines, the same. Ages can be heterogeneous. So as we discussed, ages are relationship. It can be heterogeneous, means they are combining multiple types of data from the different types, multiple ages between same vertices. So there is possibility from the same vertices, multiple ages, okay, because in a single age, we can have multiple attributes with multiple types. So there is a possibility of that we can have a multiple ages between the multiple vertices. So the key primitive is the traversal queries. Traversal query is A connected to B. This is very important concepts in the graph model. Traversal queries is A is connected with to B. So which vertex is reachable from S? S is another vertices satisfy property P. So this is called transitive closure basically. So we are looking for approaching or connecting the two different vertices on a third vertices based on a certain condition. It's called a transitive closure. Why it's so special? Relational models cannot relatively express reachability. Okay, so this is the main difference in why it's need coming to existence. In the relational model, we don't have any reachability. It's unknown number of hopes. So documents models has no native graph queries, and why it's different from the document. So in the document model, we don't have a native query, graph queries. So that's why the need of this graph model come into the existence or come into the picture. So what are the examples? I mean, which databases are mainly using the graph model, which we have seen like Neo4j, properly graphs, RDFs or Turtle. So RDF is a resource description framework. In Turtle is in its syntax. So triple store. Triple store is nothing. Subject, predicate, and its object. It's a semantic web. Use cases like a social network, road networks, biological pathways, knowledge graphs in AI in modern era. So these are some of the models of the logical data models. We started from the key value pair A. In B, we discussed document model. Then we discussed relationship model, and the fourth one is a graph model. Now we are quickly see the comparison of all these models and different aspects like model schema in relationship scalability, and what is the best case of this certain logical data models and where we can apply this. If we see here, the first one relational model is strict or enforced. We said rigid, okay, because this one schema is predefining in the relational database management system, RDBMS. So relationships are basically working on a foreign keys, one to many to many. We already discussed the modeling strategy. And scalability harder. It is horizontally scaling, it's not vertically, and it's best for the structured data and complex queries in ACID. ACID is basically atomicity, consistency, isolation, and durability, which we will discussing in the next lecture. That is transactions. So in the transactions, we are discussing these three concepts. So ACID is basically useful for the relational model, which is nothing. The use cases of this relational database management system is MySQL, MariaDB in PostgreSQL. We have the second model, document model here, which is using by the MongoDB, and that is schema flexible. We call them. Okay, here we don't have any predefined schema. If even we can easily extend them. So what are the relationship here? So we discuss here the main concept embedded is applying here, but they are also using embedded reference style, also relationships. So they can do the embed to multiple entities in a single document, or either they can reference between the entities or the collections. Scalability is quite easier, so it can scale very easy, not like the relationship model. And it is based for the hierarchical, semi-structured, or it's OOP interoperation like object-oriented programming. So graph, it is also flexible. It is native edges. I mean, the relationships are basically working on edges, as both of the above, they don't have any kind of support for the relationship like graph-based queries, not relational, not documents. So it's different from both of them. And scalability is moderate, and it is best for the connected heterogeneous data traversal. The last but not least, key value. So its schema is done. I mean, there is no schema concept. As we discussed, this is basically working on a cache. And relationships are none here also. The scalability is very high because it is in memory or in a cache level. So, I mean, it's best for the cache, temporary data, or simple lockouts. The key idea here, the NoSQL moment emerged as a reaction to the relational model's rigidity. Okay, what NoSQL means, it says MySQL, like MariaDB or Postgre, many more flavors of this MySQL or SQL. After that, they see the NoSQL moments emerge as the reaction to the the relational model rigidity, like strict schema, horizontal scaling difficulties. So that's why NoSQL concepts introduced. In NoSQL, we say there is no tables and no foreign keys and reference keys like that, but we are defining a document which is a flexible have a schema, or we can say schema-less. So that's why they give them the name of NoSQL trades, some reliability guarantee for their flexibility and scalability. And as we can see in the comparison, it can easily scale in comparison to the relational. Okay, now we are in the last model, which is the on level of the abstraction. It's released and it's almost on the computer based, how the data is represented and stored in the computer. But before starting like the physical data models, we are discussing its storage formats. Then we are discussing what is row oriented versus column oriented format storage. And then we are starting there certain types of physical data structures, like how in computer these data are stored. From them, we are discussing hash tables, okay, B trees and LSM trees and Bloom filters. And this will be the end of the lecture. Okay, physical data models, storage formats are multiple formats we have for storing the data, starting from the JSON. So its type is text and is used by document model in keynotes, no built-in schema, widely used, support nested structure. Okay. And BSN binary. So BSN binary JSON or JavaScript object notation. So its type is binary. It's mainly used by the document MongoDB. So binary encoding of a JSON, faster input output, and that is the main keynote of the BSN. CSV file, comma separated value. Its type is text. And used with the relation model. Okay, so the keynotes are here, rows and columns. No data types defined here, so we don't have any data types here. It's mainly separated by comma separated values. It is really important nowadays in AI applications. So most of the data has been stored in this one format or data science. XML, it is a text. So also like the same is used by the document model. So it is using the hash schema. So we were discussing this kind of data structure after studying the storage formats. What is a hash schema? Or what is a hash data structure? So it is a schema, XML schema, less common than JSON today. I mean, it is more like a JSON, but it's less famous like or less in use as a JSON nowadays. Okay, SARD is also an XML based. So it is a relational used with the relational models mostly. Standard archival format for the relational databases. The second last is in3 or notation 3. It is also text based and it's used with the graph RDF resource description framework. So subject predicates and object. So we have a subject based on a certain condition. We are moving over the edges to object, and its syntax is using the turtle used in the semantic web. So packet is a binary or columnar. So it is mainly used by relational or nowadays the most advanced data management system distributed. So Apache standard like Spark, Duck, DB or Pandas like Python. So excellent compression, and they have a very well compressions. So these were some of the storage formats of physical data storage. Before introducing, we should have to introduce two important concepts in the physical data models, that is row-oriented versus column-oriented storages. Okay, after that, we are going step by step. What are the data structures in the local data, in the physical data models? Data input, data layout. So we are discussing the row-oriented and column-oriented, okay? In the left side, we have on the column aspect. What is the aspect like data layout? What is the best for used by, and its compression and column aggregation. So if we take out the row oriented, what is the data layout? Each row stored contiguously. So rows are contiguously like row oriented. In the column oriented, or each of them are column contiguously stored. So what is best for row-oriented is accessing the whole record online transactional processing. So it's mainly using for OLTP, like recording the whole records, online transactional processing. The column-oriented example in the above, we already discussed Parakeet. So the aggregating columns, average, sum, correlation, it is useful for the online analytical processing. So this is having a two different usage of the row oriented and a column oriented. So one of them is for the transactional processing, and the second one is analytical processing. Like analytical is more memory consuming. Okay, which one storage system is used by which technology? So like row-oriented is mostly used by RDBMS, relational database management system like PostgreSQL, MySQL, or any other flavors of MySQL. But which technologies are using column-oriented? Like they are using by Pandas, Spark, DuckDB, Data Warehouse. In these are the multiple technologies which are using the column-oriented uh, storage system. Compression lower because the data are heterogeneous. If you see on the row level, let's suppose we have taken an example of the applicant or something else like their personal details, name, okay, father name or surname and date of birth, age. So if you take it like in a column wise, and multiple people. So in a row wise, the data is all of them are heterogeneous, changes data, okay, per block. But here in the column oriented, the compression is high. Why? Because in a single column, we have a single type of data. So higher homogeneous types per column. That is the main difference. In column aggregations must load all block. So how they are column wise aggregating. So row oriented it's quite slow because they are loading all of the blocks. But in the column oriented storage, there is only relevant columns. So it's very fast. And last but not least, disk versus SSD. And disk seek time is 10 milliseconds plus rotational latency. It is 5 milliseconds plus transfer. So here seek times is dominating the co-located data access together in the same disk in the same blocks. So SSD is a voltage-based flash access, which is essentially random access and parallel rates of set overhead. So in comparisons of these two different storage system of disk and SSD, SSD is definitely faster, especially for the column oriented. It's also a main differentiations of both of them to understand about the disk and SSD. Now we are moving towards the concept of the data, like physical data storage so structures, actual structures of physical data. We started with the conceptual, then we discussed the logical, and in the logical after we studied physical data structure, but before that we studied its formats and its storage system of the row oriented and column oriented. The first one is a physical data structure is hash table, as we have seen this in the previous discussions of the XML. Yeah, in the XML, not in the XML, but we discussed this here, hash. Okay, and yeah, XML. XML is basically a text base, so it's usually used with a document model, and it's using a hash schema. So from the hash schema, XML schema less common than the JSON today. So here, if you see, this is the hash schema or the hash table, a kind of a data structures. So how they are storing the XML type of data. So hash tables are two arrays. One of them is for key and one for values, like key value pairs. So hash function maps key and indexes. The main difference with the key value model, if you see in the logical, that's actually a logical model, but this is a data structure. Over there we have key value pairs, but here we have one of them is for the keys, okay, and one of them is for the values. But here these keys are using a hash function maps and indexes here. That is the main differentiation with the key value. Okay, how the CRUD complexities are working. CRUD means like create, read, update, and delete. Complexity, big O notations represent the complexities. It is one on an average, which is very good. And as we are going further, so it is becoming ON or O login in the worst case, which is the best in the worst scenario, the big O notations login. As cache values equals to actual data in memory, okay, as indexes values are storage addresses. So caches are the values which have holding the actual data in the memory, but indexes are the storage addresses of the values. So limitations, it is a poor resistance, no range queries. So we will discuss what is no range queries here in mainly the B trees, which is one of the limitation. Then further why B trees come into the picture. So no range queries, it is mainly for in memory or cache use. So this is the hash table and how it works with the use of the hash functions. Now we are discussing the B trees. B trees is another data structure, a physical data structure. B trees is this the dominant data structure for disk-based indexes. in RDBMS, Relational Database Management System, a balanced tree where each non-root or non-leaf node has a T1 to 2T1 keys, or T is nothing but it is an order. So in keys in a node, so it is mean n plus one. In keys in a node means like if a certain node has a key, so their leaf or children should be n plus one. So keys are stored in ascending order. So C1 is a pointer in key one is a K. So C1 is less than or equals to K1 and K1 is less than or equals to C, a two pointer and less than or equals to dash dash dash. We are going on. Okay, so we are furthermore node size is equals to storage blocks and it's flat tree. In the worst case scenario, the accessing of the disk is very complex per operation. So based on this flat tree, they are basically solving the main problem. We are taking the whole storage block as a flat tree or fat tree. Both of these names are used for them. So operations are read. All of the complexities are listed down here or in the worst case scenario, or most of them are O, big O notations login. We are discussing the operation, its complexity, and its algorithm summary. When we are applying read, so its complexity is automatically for all of them in the worst case, uh, big O notation. Okay, in the read navigate root to leaf, following order keys return value if found. So that's why if we are reading certain things from a B trees, so they will going from the node to the end of leaf, and if they found, so they will return. So that's why in the worst case, if the tree is very long, so it will be really difficult and accessing. Insert navigate to leaf. So starting from the leaf, insert a full. So if it's full, then they will further split them, leave it a median. So propagate median up, rebalance recursively. So that's why in the worst case scenario, if it's full, so that's why it will be complex, and its complexity is a big notation or login. Delete leave. So when we are deleting, so it's leave or internal, and remove the key in the leave case. So rebalance them, try right and left and right rotations. If neither possible, merge sibling them. And the delete internal, replace with the largest key of the left child or small of the right child, both in leaves, then rebalancing them. The last one, lazy delete, which is important with an efficient when few relates we are using. So it's flagging them only, delete them without restructuring. The main differences with the hash table here is they are supporting range queries efficiently and consecutive keys, which is mean like consecutive storage addresses. So we have seen that here the consecutive keys here, a node size is equals to storage block. So we are holding here a complete block. So that's why they are supporting range queries very efficiently and having all the keys and pointers. So they can consecutive storage addresses. And based on this, it's really important as compared to the hash table. Now we're introducing the third type data structure, LSM tree. LSM tree is a log structured merge tree, alternative to B trees. It is like the most to them, but it is more optimized for write heavy workload. That is good for the read heavy, and this is for the write heavy workloads. Two components, SSTs. SSTs is nothing but sorted string tables. It is time-stamped, append only the log files on a disk. When we are writing something, so they are only appending the log files. In memory trees, we are using here in memory the B trees. So B trees indexes a subset of a key for fast access. So for the subset, for the subset indexes, we are using the B trees. Its idea is for fast accessing. So we have a operations like create, update, delete, read, and compaction. So and what is the behavior? So when you are creating, so append new key value pair to SST log. SST is nothing but sorted string tables. Actually, LSM is working by integrating the B trees. So B trees we are using in the in-memory tree, so which is for the fast indexing. Okay. When we are deleting or updating, so do not modify old values, only append new entry or deletion mark. And the read operations, so check in memory structure first, then then SST sorted strings tables from a newest to oldest. So this is the idea, and the compaction, so periodically apply updates and deletes and merge SSTs synchronously or asynchronously to avoid the plot. Here is a short comparisons of the B trees versus LSM trees. In the B trees, the read speed is faster. As we see, that is read heavy, and this one is write heavy LSM. So for the read speed, the LSM is slower. So check multiple SSTs, sorted strings table, okay? In the sorted case, so they should have to go sequentially. In the write speed, B3 is then slower in place of rebalancing because they should have to rebalancing while you are writing on them, as we have seen in the operations of the insert. So navigate to leave insert. Okay, navigate to leave insert a full split them, leave at a median and propagate the median up, rebalance recursively. So this recursive operations is very complex. So that's why it's slower in the B trees, the write speed, but LSM is much faster. It's only basically appending the SSTs. Okay. And here you can see the create, and we are appending the new keys value pair to SST log only. In the last one, what's the best usage for of the B trees and LSM? So best for read heavy workload, and LSM tree is best for the write heavy workload. The last one we are discussing here, that is the Bloom filter, and this is the last of the lecture, the data structure. Okay, a probabilistic data structure that answers is K key present. So that's why it is basically solving, it is addressing the gap between the B trees and LSM trees. LSM tree is long structure merge tree. So Bloom filter is working among both of them and addressing their whole idea. Used to skip unnecessary disk lookup. So they are only searching for SK or k-mean key present. So how they are working, structure array of embeds plus the hash function, and insert create, apply all h hash functions to k and set corresponding bits to 1. So when the query reads starting, so apply all h hash functions to k, and if all bits equals to 1, so probably present. So they will say yes, it is present, and any bit equals to 0, definitely they will say it is an absent. So last property, we are saying here false negative in the creation case, and detail says impossible. Why? Because if absent always is an absent, so that's why it's called false negative in the creation case. If the return of that one, the impact is 0, I mean, there's no key value is available. False positive is read, and in the read conditions possibly, but small probability may say presence when key is absent. In some cases, that's why it is a probabilistic data structure. And the delete case, I mean, delete a key, delete support, not directly supported. Counting Bloom filters variants adds it, but may introduce false negative. So that is the overall core idea of the Bloom filter, and what's false negative, false positive, and how the read property and creation property applies here. So this is the mainly gap between these two data structures of the B trees and LSM trees. They do not look up for unnecessary I mean, memory for, they just ask one question, SK key is available. And this is how they are structuring the array of embeds and hash function. They're applying the insert and create them, and based on that they are queuing them if the one is available. So they say probably it's present, and bit zero definitely it's an absent. So this is all about the data models. So in short summary, if we go again, so we started with the discussions of the three different levels of models: conceptual models, logical models, and physical models. And the physical model, the conceptual model, we only discuss entity relationship diagram and its relationship. In the logical model, we discuss key value model, document models. We discussed relationship model and graph model, and the short comparisons of all the logical models. Then in the physical models, we discuss storage formats, we discuss row oriented versus column oriented, and at the end we discuss four types of the data structures: hash tables, B trees, and LSM trees, and Bloom filter. Bloom filter is nothing but it is addressing the gap between the LSM and the B trees. So this is all for this lecture. Thank you. Bye.